So now we're on to our last and final example, which is going to be creating a recurrent neural network play generator. Now this is going to be the first kind of neural network we've done that's actually going to be creating something for us. But essentially what we're going to do is make a model that's capable of predicting the next character in a sequence. So we're going to give it some sequence as an input, and what it's going to do is just simply predict the most likely next character. Now there's quite a bit that's going to go into this, but the way we're going to use this to predict a play is we're going to train the model on a bunch of sequences of text from the play Romeo and Juliet, and then we're going to have it so that we'll ask the model, we'll give it some starting prompt, some string to start with, and that'll be the first thing we pass to it. It will predict to us what the most likely next character for that sequence is, and we'll take the output from the model and feed it as the input again to the model and keep predicting sequence of characters. So keep predicting the next character from the previous output as many times as we want to generate an entire play. So we're going to have this neural network that's capable of predicting one letter at a time actually end up generating an entire play for us by running it multiple times on the previous output from the last iteration. Now, that's kind of the problem. That's what we're trying to solve. So let's go ahead and get into it and talk about what's involved in doing this. So the first thing we're going to do obviously is our imports. So from keras.preprocessing, import sequence, import keras, we need TensorFlow, NumPy, and OS. So we'll load that in, and now what we're going to do is download the file, so the data set for Romeo and Juliet, which we can get by using this line here. So Keras has this utils thing, which will allow us to get a file, save it as whatever we want. In this case, we're going to save it as shakespeare.txt, and we're going to get that from this link. Now, I believe this is just some like shared drive that we have access to from Keras. So we'll load that in here, and then this will simply give us the path on this machine, because remember, this is Google Collaboratory, to this text file. Now, if you want, you can actually load in your own text data, so we don't necessarily need to use the Shakespeare play. We could use anything we want. In fact, an example that I'll show later is using the B-movie script, but the way you do that is run this block of code here, and you'll see that it pops up this thing for choose files. Just choose a file from your local computer, and then what that will do is just save this on Google Collaboratory, and then that will allow you to actually use that. So make sure that's a text file that you're loading in there, but regardless, that should work, and then from there you'll be good to go. So if you don't need to do that, you can just run this block of code here if you want to load in the Shakespeare.txt, but otherwise you can load in your own file. Now, after we do that, what we want to do is actually open this file. So remember, that was just saving the path to it. So we'll open that file in RB mode, which is read bytes mode, I believe. And then we're going to say .read. So we're going to read that in as an entire string. We're going to decode that into UTF-8 format. And then we're just printing the length of the text, or the amount of characters in the text. So if we do that, we can see we have the length of the text is 1.1 million characters approximately. And then we can have a look at the first 250 characters by doing this. So we can see that this is kind of what the play looks like. We have whoever's speaking, colon, then some line, whoever's speaking, colon, some line, and there's all these break lines, so \ns, which are telling us, go to the next line, right? So that's going to be important because we're going to hope that our neural network will be able to predict things like break lines and spaces, and even this kind of format as we teach it more and get further in. But now it's time to talk about encoding. So obviously all of this text is in text form. It's not pre-processed for us, which means we need to pre-process it and encode it as integers before we can move forward. Now, fortunately for us, this problem is actually a little bit easier than the problem we discussed earlier with encoding words, because what we're going to do is simply encode each character in the text with an integer. Now, you can imagine why this makes this easier, because there really is a finite set of characters, whereas there's kind of a indefinite, or I guess infinite amount of words that could be created. So we're not really going to run into the problem where two words are encoded with such or two characters are encoded with such different integers that it makes it difficult for the model to understand, because and we can look at what the value of vocab is here. We're only going to have so many characters in the text, and for characters it just doesn't matter as much because an R isn't like super meaningful compared to an A, so we can kind of encode in a simple format, which is what we're going to do. So essentially, we need to figure out how many unique characters are in our vocabulary. So to do that, we're going to say vocab equals sorted set text. This will sort all of the unique characters in the text. And then what we're going to do is create a mapping from unique characters to indices. So essentially, we're going to say UI for IU in enumerate vocabulary. What this will do is give us essentially 0, whatever the string is, 1, whatever the string is, 2, whatever the string is, for every single letter or character in our vocabulary, which will allow us to create this mapping. And then what we'll do is just turn this initial vocabulary into a list or into an array so that we can just use the index at which a letter appears as the reverse mapping. So going from index to letter rather than letter to index, which is what this one's doing here. Next, I've just written a function that takes some text and converts that to an int, or the int representation for it, just to make it a little bit easier for us as we get later on in the tutorial. So we're just going to say np.array of, in this case, and we're just going to convert every single character in our text into its integer representation by just referencing that character and putting that in a list here, and then obviously converting that to NumPy array. So then if we wanted to have a look at how this works, we can say text as int equals text to int text. So remember, text is that entire loaded file that we had above here. So we're just going to convert that to its integer representation entirely using this function. And now we can look at how this works down here. So we can see that the text for citizen, which is the first 13 letters, is encoded by 18, 47, 56, 57, 58, 1. And obviously each character has its own encoding, and you can go through and kind of figure out what they are based on the ones that are repeated, right? So that is how that works. Now, I figured while we were at it, we might as well write a function that goes the other way, so into text. The reason I'm trying to convert this to a NumPy array first is just because we're going to be passing in different objects potentially in here. So if it's not already a NumPy array, it needs to be a NumPy array, which is kind of what this is doing. Otherwise, we're just going to pass on that. We don't need to convert it to NumPy array if it already is one. We can just join all of the characters from this list into here. So that's essentially what this is doing for us. It's just joining into text. And then we can see if we go into text, text is int :13, that translates that back to us for citizen. I mean, you can look more into this function if you want, but it's not that complicated. Okay, so now that we have all of this text encoded as integers, what we need to do is create some training examples. It's not really feasible to just pass the entire 1.1 million characters to our model at once for training. We need to split that up into something that's meaningful. So what we're actually going to be doing is creating training examples where we have the first, where the training input, right? So the input value is going to be some sequence of some length. We'll pick the sequence length. In this case, we're actually going to pick 100. And then the output, or the expected output, so I guess like the label for that training example, is going to be the exact same sequence shifted right by one character. So essentially, I put a good example here. Our input will be something like hell, right? And then our output will be ELLO. So what it's going to do is predict this last character essentially, and these are what our training examples are going to look like. So the entire beginning sequence, and then the output sequence should be that beginning sequence minus the first letter, but tack on what the last letter should be. So that this way we can look at some input sequence and then predict that output sequence, plus a character, right? Okay, so that's how that works. So now what we're going to do is define a sequence length of 100. We're going to say the amount of examples per epoch is going to be the length of the text divided by the sequence length plus 1. The reason we're doing this is because for every training example, we need to create a sequence input that's 100 characters long, and we need to create a sequence output that's 100 characters long, which means that we need to have 101 characters that we use for every training example, right? Hopefully that would make sense. So what this next line here is going to do is convert our entire string data set into characters. And it's actually going to allow us to have a stream of characters, which means that it's going to essentially contain 1.1 million characters inside of this tf.dataset object from tensor slices. That's what that's doing. Next, so let's run this and make sure this works all right. What we're going to do is say sequences is equal to char dataset.batch. Sequence length is the length of each batch. So in this case, 101. And then drop remainder means, let's say that we have 105 characters in our text. Well, since we need sequences of length 101, we'll just drop the last 4 characters of our text because we can't even put those into a batch. So that's what this is doing for us, is going to take our entire character data set here that we've created and batch it into a length of 101. and then just drop the remainder. So that's what we're going to do here. That's what sequences does. Now split input target. What this is going to do essentially is just create those training examples that we needed. So taking these sequences of 101 length and converting them into the input and target text, and I'll show you how they work in a second. We can do this, convert the sequences to that by just mapping them to this function. So that's what this function does. So if we say sequences.map and we put this function here, that means every single sequence will have this operation applied to it, and that will be stored inside this dataset object. Or I guess you'd say object, but we'll also just say it's going to be, the variable, right? So if we want to look at an example of how this works, we can kind of see. So it just says example. The input will be first citizen. Before we proceed any further, hear me speak. All speak. First citizen you. And the output, notice the first character is gone, starts at I. And the last character is actually just a space here, whereas here it didn't have a space. So you can see there's no space. Here there is a space. That's kind of what I'm trying to highlight for you. The next example, we get are all resolved rather to die rather than fam, whatever. It goes to here, right? And then we can see here we omit that A, and the next letter is actually a K, right? That's added in there. So that's how that works. Okay, so next we need to make training batches. So we're going to say the batch size equals 64. The vocabulary size is the length of the vocabulary, which if you remember all the way back up to the top of the code was the set or the sorted set of the text, which essentially told us how many unique characters are in there. The embedding dimension is 256, the RNN units is 1024, and the buffered size is 10,000. What we're going to do now is create a data set that's shuffled. So we're going to switch around all these sequences so they don't get shown in the proper order, which we actually don't want. And then we're going to batch them by the batch size. So if we haven't kind of gone over what batching and all this does before, you can read these comments. This is straight from the TensorFlow documentation. What we want to do is feed our model 64 batches of data at a time. So what we're going to do is shuffle all of the data, batch it into that size, and then again, drop the remainder if there's not enough batches, which is what we'll do. We're going to define the embedding dimension, which is essentially how big we want every single vector to represent our words are in the embedding layer. And then the RNN units, I won't really discuss what that is right now, but that's essentially how many. It's hard to really I'm just going to omit describing that for right now because I don't want to butcher an explanation. It's not that important. Anyways, okay.